The topic of this video will be how we study chemical reactions. The overall reaction equation tells us what happens. It tells us the reactants, the products, and any other inputs that are necessary to make the reaction occur, such as light or heat. The reaction mechanism tells us how it happens. It tells us which bonds break, which bonds are made, and in which order this happens. Reaction mechanisms are the main focus of organic chemistry. The thermodynamics of the reaction tell us which compounds are favored energetically at equilibrium. Thermodynamics deals with Gibbs free energy, enthalpy, entropy, and the equilibrium constant. This is mainly a review from general chemistry, so we won't spend any time in class on this. The final piece of the puzzle is kinetics, how fast the reaction occurs. Kinetics involves the rate constant and the rate of the reaction. Again, this is a review from general chemistry, and we won't spend too much time on this, although I do want to briefly talk about the rate constant and it's dependent on temperature, among other things. The rate constant is constant for any specific reaction, and we can calculate it using the Arrhenius equation. The rate constant is equal to A times E raised to the negative EA over RT. Let's talk about what all these symbols stand for. A is a constant, and it's called the frequency factor. We're not going to worry too much about that. E is the base of the natural logarithm. The terms we're really interested in are E sub A, known as the activation energy, and T, which stands for temperature. R is another constant, specifically the gas constant. Again, we're not going to worry about that right now. Specifically, we're interested in the activation energy. The rate constant, or the speed of the reaction, is dependent on the activation energy and temperature. The activation energy represents the change in energy between reactants and the highest energy state that occurs during the reaction. This is known as the transition state. The transition state is very unstable and cannot be isolated. We can look at the energy changes during a reaction using something called a reaction coordinate diagram. A reaction coordinate diagram shows us the energy changes throughout the entire reaction as it occurs, and so it's a graph with energy on the y-axis and the reaction coordinate on the x-axis. The reaction coordinate being the point that we're talking about within the reaction going from reactants to products. So let's look at a specific example. We will look at the reaction of reactants A and B reacting to give us products C and D. This reaction is exothermic, meaning that the products will be lower in energy than the reactants. We can indicate this on our reaction coordinate diagram. Reaction coordinate starts at the reactants and ends at the products, which will be lower in energy than the reactants. The difference in energy between the reactants and the products is delta H, the change in enthalpy. We can also mark the position of the transition state, which will be between the reactants and the products, and will be the highest energy state that occurs. The transition state is often indicated by a double dagger. We can fill in the rest of the reaction coordinate diagram because we know that the energy will slowly increase as we approach the transition state and then decrease as we approach products. The activation energy is the difference in energy between the transition state and the reactants. This is the complete reaction coordinate diagram for the reaction of A plus B goes to C plus D, which is an exothermic reaction. This is a reaction that has only a single step and no intermediates. What about a reaction with more than one step? This reaction coordinate diagram will be more complicated and will contain intermediates C and D. We will again assume that this reaction is exothermic. We will start with reactants A and B. Reactants A and B will react and produce a transition state. We'll call this transition state 1. And then we'll form intermediates C and D, which will be lower in energy than the transition state but higher in energy than the reactants. Typically, the intermediates are higher in energy than the reactants or the products, although not always. Intermediates C and D will react to give us the products, and we'll go through a second transition state, which in this case I've drawn at a lower energy than the first transition state, although the reverse can be true. And finally, our products E and F, which are the lowest energy point of my reaction. There are a couple of important values that we can find on this reaction coordinate diagram. The first is the activation energy for the first step, which is the difference in energy between transition state 1 and the reactants. The activation energy for the second step is the difference in energy between the intermediates C and D and the second transition state. The difference in energy between the reactants and the products are the change in enthalpy. We can also determine the difference in enthalpy between the reactants and the intermediates, and the difference in enthalpy between the intermediates and the products. In this case, step 1 acts like a bottleneck because it is the highest energy transition state and produces or requires the largest activation energy. We call this bottleneck step the rate determining step. The reaction, the overall reaction, cannot proceed any faster than its slowest step, which in this case is the first step. The reason that we study the mechanism, the thermodynamics, and the kinetics of a reaction is because these things help us to predict the products and can also tell us how to get the products that we want. This is very important in organic chemistry.